Hi all, this is a short video to address the need to use limit notation and why it's important not to lose that limit notation as you do your work. Some of you have lost a few points on your homework or quiz because you've dropped the limit notation and you might be wondering why. So here is a quick little explanation. On the left-hand side of the screen here, you see I have worked through one of the homework problems showing the correct way with the limit notation all the way down through. And on the right-hand side, you've seen you see where I've worked through the problem, but I kind of lost the limit notation for a little while. And this happens, we get tired of writing it out, so we just kind of leave it. We know we really are going to take the limit eventually, so we'll put it back in eventually. But for now, we're just going to leave it out because we don't want to write it all out there like I have on the left. And the problem with that is the use of setting up things equal to each other. And so when you're saying that one thing is equal to another thing, that means that they are totally equivalent. And so here, all the way down on the left-hand side, you can see I'm saying, okay, well, I need to take the limit of this expression. So the first thing I need to do before I can take the limit is I need to rearrange that expression a little bit. I need to simplify it. So I multiply out my x plus h squared, and I get to this point. But I still need to take the limit of that. Okay, so I have to say I'm taking this, all of this is equal to all of this. I haven't lost any information anywhere along the line. Then when I come down to my next step, again, I'm just working with that expression, trying to simplify it so that I can take the limit. And so everything you see here is equivalent to everything I had in the line above it. It's just simplified, but it's equivalent. Same thing here. I'm finally down to this step. This step, very close to the end here. And so now, even though this looks much smaller, much simpler than what I had up here, it's still equivalent. They are still equivalent to each other. The limit of all of that is equivalent to the limit of all of this. So I'm keeping that equivalency. And then I simplify one more time, and I'm finally down to this I'm going to say simple, very simple expression that I can then take the limit of. So again, I haven't changed anything. I still have that equivalency going on. Now I can actually take the limit. So now I'm going to say, okay, the limit as h goes to 0 of 4x plus 2h, well, as h gets closer and closer to 0, this term becomes very insignificant, almost like it's not even there, it disappears. And so the limit as h approaches 0 of 4x plus 2h equals just 4x. It doesn't equal the limit anymore of that. It just equals that value. The limit of all of this is equal to this final value. So now is why I don't have my limit notation anymore, because I'm not going to take the limit of just 4x. 4x is the limit. They are equal. If we look over on the right-hand side, we have a little bit of a problem because just like on the left side, I have my initial expression. I'm taking the limit of all this stuff. And then, unfortunately, on the very next line, I am no longer taking the limit. I am just saying that the limit of all that stuff is equal to all that stuff. And that's not true. The limit of the stuff is not equal to the stuff. And so therefore you have a falsehood. And in mathematics, when you're writing out your mathematics, you cannot have falsehoods in the equal signs. So that is why it's important that we have that limit notation in there, because that's the only way that that equal sign, and even if you don't put the equal sign, you're implying that they're equal as you work down the steps. But the only way you can do that is to set up that equivalency is if they're actually equal. So in all of these cases, we need the limit as h approaches 0 of the expression, not just the expression.